Good evening, all. I'm Kirtana Priya from Vellore Institute of Technology. So, my topic is based on hydrothermal synthesis, characterization, and DFT investigation on rare earth doped with WICQ for the thermoelectric application. So, these are the roadmap we are going to look into it. So, thermoelectric materials, hydrothermal synthesis, DFT, and structural. Group 6, which has high tensile strength and lowest coefficient of linear thermal expansion, and selenium is a semiconducting material which can easily convert according to the temperature change. As for rare earth, it's a trivalent compound. They can create the lattice strain. This also can influence the band structure, carrier effective mass, density, and the states near the Fermi level, which gives a better performance for thermoelectric performance. This is the simple hydrothermal synthesis I did for WIC2. So these are the results. Structural analysis, XRD analysis. First, in this we can prove that it's an hexagonal structure, and we get the average crystal size of 40.35 nanometer. These are the wave number and functional group I found from the FTIR analysis. From UV visible spectroscopy, we come to a conclusion that WIC2 is a direct band gap which has 2.05 electron volt. This shows the strong UV visible absorption at 555 nanometer in the top plot, which is suitable for medium temperature thermoelectric application. This also has a high Seebeck coefficient, and Peltier shows the cooling. Moving on to the DFT insights, we have electronic band structure and UOS, thermoelectric power factors of electronic thermal conductivity of monolayer WIC2, lattice thermal conductivity of monolayer SE2, and figure of merit. Here, crystal hexagonal structure of the space group P6M2, and this shows the strong bonding between strong covalent bond between W and SE2 atoms, which is sandwiched between where tungsten is sandwiched between two selenium atom layers. Electronic band structure, here monolayer SE2 has the direct band gap, which has by 1.56 electron volt. Here here the conduction band is minimum and valence band is maximum, which occurs at the same line. Seebeck coefficient is calculated at the room temperature of 350 units, and this indicates the voltage generation from temperature differences, and this shows the high Seebeck coefficient, which contributes the higher thermoelectric figure of merit. The power factor, which is given by PF is equal to I square into sigma. From this, power factor is increases with temperature and carrier concentration, and this shows the n-type semiconductor. This also indicates the electron doping is more favorable for thermoelectric application. Moving on to the lattice thermal conductivity, here WiC2 exhibits low lattice thermal conductivity with higher and the heavier tungsten atom has lowers the phonon frequency. This also reduces the velocity group due to the heat suppression, heat transport, and the low thermal conductivity is desirable because it increases the thermoelectric efficiency. As for the result, monolayer WiC2 exhibits higher ZT, which is also n-type doping, gives the best performance, and this is excellent for thermoelectric application with a wide temperature range. So from this, WiC2 shows that it is a promising thermoelectric application. My ongoing work is I'm currently measuring the key thermoelectric parameters across the temperature range synthesis WiC2, and also evaluating the stability and output under bending conditions of variable generator using our body heat prototypes, and how dopants are influencing the electrical and thermal properties through the standard electrical measurements. Thank you.
Questions?
Your samples are thin films or bulk samples?
They are not bulk samples, sir.
Bulk samples?
No, they are not bulk.
And what, thin films?
Thin films.
How you prepare WSE2?
By simple hydrothermal synthesis.
And what is the figure of merit of this material?
Here we got with this only we got the band gap of 1.56 electron volt. We are calculating ZT, sir.
But you will prepare powder samples.
Yeah, powder.
So they are bulk. I mean, what thin film?
We still didn't figure out, since we are doping rare earth into it, so it is taking time to figure out what sort of sample it is. So far WSC2 is prepared, and we are waiting for the results of rare earth.
Any more questions?
Well, if not, then let's thank the speaker and.
Thank you.
First of all, I would like to thank organizers for this kind of invitation. And so myself, Pankaj Gupta, I work with Professor Surjit Singh at IISER Pune. So I work on SNT based thermoelectric materials. Here in my talk, I would like to tell about my strategy about for increasing thermoelectric properties of these SNT based thermoelectric materials. Here I have try two approaches to increase the thermoelectric properties. So first one is the zinc-indium co-doping to improve its concentration, carrier concentration, and on the top I have tried to alloy to improve its thermal properties. So these are my brief outline. So I will first I will give a brief introduction to thermoelectricity. Then I will come to the point that why I chose SNT as my thermoelectric material and the motivation behind that. Then I will briefly tell about the synthesis method and the key characterizations. Then I will discuss about the results, and then I will summarize my talk. So what is thermoelectricity? So thermoelectricity is a direct conversion between heat and electricity. So what kind of heat? It can be any kind of heat that is getting wasted in, like you may say that the heat, thermal power plant, nuclear power plant, even the heat generated in your CPU, GPU, all these heats where it is getting generated, getting wasted, there we can use the thermoelectric material to convert heat into electricity, useful electricity. So what is the principle behind this thermoelectric? So the basic principle behind the thermoelectricity is the Seebeck effect. How it works? Suppose you have a semiconducting material, you heat one end and cool one end. There is temperature difference. So what will happen that the carrier will start moving from high temperature to low temperature, and hence it will happen till the point that the potential developed at the other end is going to oppose the motion of the carriers. So the potential difference will depend on the temperature gradient. The ratio is given as the Seebeck coefficient, that is the material characteristics property. But what is the thing which define the goodness of a thermoelectric material and hence its conversion efficiency from heat to electricity? So the goodness of a thermoelectric material is decided by this dimensionless figure of merit, that is called GT. That is a complex function, that is a function of Seebeck coefficient, electrical conductivity and the thermal conductivity. So what is happening here, that Seebeck, this thermal conductivity can be further broken into these two parts, that is thermal conductivity and the electrical thermal conductivity. If you see, this tuning is not easy because all these parameters are dependent on the interdependent on the carrier concentration. As you can see from this plot as well, that everything is dependent on the carrier concentration and we need some certain optimized carrier concentration to get higher ZT. So, but one thing is there, that good thing is there, that this KL is a phonon KL, that is the lattice part of the thermal conductivity, depends on the phonon scattering. So by tuning this carrier concentration and tuning this lattice thermal conductivity, we can get good thermoelectric properties. So in thermoelectrics, what we look for? We look for a material which has metal like high electrical conductivity and a glass like low thermal conductivity. And getting this is very challenging. So what we choose? We choose a semiconductor material where we are having moderate electrical conductivity, low thermal conductivity, and we can tune the electrical conductivity further by some doping, as we all know in semiconductors. So why I chose SNT? So previously people have reported, people have explored a lot about the excellent thermal properties of PVT, but PVT and SNT are having the same structure. Even though SNT is not having good thermoelectric properties. Why? The reason behind that is these numbers. These numbers are the numbers, this delta is the band offset, meaning the band offset between the light hole and heavy hole bands. If this band offset is very low, meaning this band is also contributing in the transport, and hence the density of state will be very high, and the density of state effective mass will be very high, and this will give a higher Seebeck coefficient. But in case of SNT, we are not seeing, there is a very high band offset that is limiting its Seebeck effect, and hence it has been some problem. So we thought to explore the SNT because first of all, it is unlike PVT, it is a eco-friendly, no toxic element, and at the top this is having intrinsically high SN vacancies, meaning there is a huge possibility of tuning the carrier concentration. Low thermal conductivity because of the intrinsic void defects. Fascinating band engineering possibilities is there because you by doping something or allowing, you can tune this band structure. And it has having metavalent characteristics, meaning it has both characteristics, metallic and covalent, because SNT is having some metallic bonding character and covalent character. That is very useful from thermoelectric point of view. Previously people have reported about zinc doping, that zinc doping is going to bring some band convergence, reducing this band offset. And also people have reported that indium doping in SNT is going to bring some resonative state, that means that high density of state near the Fermi energy. And this too helps increasing density of state effective mass, hence higher Seebeck effect. Motivated by these two observation, we thought to incorporate the both effect in the same material. So for that purpose, we try to dope zinc and indium together in certain proportion. And how we did it? So for that, our synthesis method, first we took a quartz tube where we took all the precursor in and evacuated the tube by sealing it with a flame. We put in the furnace, heated it 900 degrees centigrade. We got a nice ingot. We crushed it. We did hot pressing to get a very high density pellet. And then I looked for the XRD, a picture of like phase purity of the sample, and we found that all the samples are nearly pure except some SN and zinc impurity, as you can see in the FS imaging. All the doping is following the Vegard law because of the lower size of the zinc and indium. With this allowing, we can see there is some lattice disorder in the system that is very helpful in reducing the lattice thermal conductivity. So out of these 5 samples, in the interest of time, I have put only 2 samples. That is the best one, like pristine and the best sample which I found. So what is happening here with doping? Lattice electrical conductivity is reducing a lot because of the heavy effective mass coming due to the indium, because of high density of state. that is killing the mobility, hence it is going down. But at the same time, since effective mass is very high, meaning Seebeck is very high, and hence we are getting a power factor reasonably better than the Princeton. At the same time, thermal conductivity is very low because of the fact electrical conductivity is also dependent on the thermal conductivity, and also disorder is there. We tried to export lattice thermal conductivity by using Weidmann-Franz law, that is the total thermal conductivity minus electrical thermal conductivity, and hence in this way we could increase GT figure of merit by 53%, but still there is a lot of scope to reduce this thermal conductivity a lot, because theoretical minimum value of thermal conductivity is reported to be 0.4 watt per meter Kelvin. So we thought to increase this to reduce it further. So for that purpose we came to a literature where people have reported that AGSB alloying has been reported to reduce the thermal conductivity a lot from nearly 2.5 to 1. So we thought to incorporate this effect in our sample as well. So what we did, and also at the same time AGSB alloying has been reported to bring the band convergence. Earlier this band offset was 0.3 in SNTE, if you remember. Here it is reducing 0.16, meaning more band convergence can bring more dense stable state. So for this purpose we prepared a lot series of sample, and we found XRD is very clean. All samples are single phase following the Wegert's law because of the lower atomic size of antimony and zinc, antimony and silver. There is lots of lattice disorder as expected, because there in the system there are lots of atoms presented here in there, that is bringing lots of lattice disorder. That is helpful for reducing the thermal conductivity. So here we can see that this G is equal to 0 is the optimized sample from our previous series, and after alloying we are getting initially we are getting higher electrical conductivity because of the increased carrier concentration. More alloying is reducing the electrical conductivity because the mobility is going to decrease a lot because of disorderness. And Seebeck, you can see Seebeck is increasing a lot because the density of its state effective mass is very high. And to look behind more into detail that why at the same time carrier concentration increasing but Seebeck is also increasing, we found that we plotted the Pejorenko plot, that is theoretical accepted plot, and we found that the Seebeck value is coming to be higher, meaning there is some band convergence signature and the resonant state signature that is playing a role into increasing the Seebeck values. And power factor is nothing, just a product of electrical conductivity and Seebeck square, and hence it is pretty high throughout the temperature range. Thermal conductivity is going to be low because of the high V disorder, which we can see from here. High disorder, it is going to scatter more and more phonon, hence we can get very low thermal conductivity. We tried to segregate the lattice part using the same Weidmann-Franz law, and we found it has approached nearly the amorphous limit of the sample. That is the excellent point of this work, and hence by incorporating this all effect we could get a GT of around 165% enhancement in the overall GT. And here you can see I have done a systematic study of all the sample, and we could increase GT and average GT. Average GT is more important because this is the GT which impact the thermoelectric device efficiency, and we could get a very huge enhancement of around 300% increment in the average GT and 165% of increment in the highest GT. This is a summary. The same, by incorporating all the effect we could get a highest GT of 1.30. This is my reference. Thank you.
Questions?
To the electronic contribution to thermal conductivity that you calculate theoretically from Weidmann.
Correct, sir.
And which is more contribution, phonons or phonon contribution is higher?
And phonon contribution is very low. Electrically contribution is very high. Because, yes, because you can see electrical contribution is very high. That's why. But due to the disorder, the phonon contribution is very, very low, because phonons are getting scattered more and more.
Disorder is due to what? Some defects or what?
Because of this mismatchment in the atmosphere size. Suppose there was uniform distribution of tin atom, and now antimony, silver, selenium, tellurium, all these disorder they are making it resolved in the system.
So in one of the slides you have shown that with increase in Z component there is an increase in conductivity. A systematic study there was.
Yeah, this one.
Yeah.
Huh.
But the sigma value of the conductivity increases at 5 and then decreases. Right. So
8.5. Yeah,
yeah. Then for 10, 15, 17.5 and all this.
it's
it is
reducing.
less than the why the sharp increase at Z equals to 5.
Because see what we are doing at the initial alloying, once we are putting 5% of AGSBTE2. So what is happening, that carrier concentration is boosting, but mobility is not getting affected that much. As we are, if we are allowing more and more, then mobility is going to drastically affect. And you know sigma is equal to n e mu. We need to play with the mu into n. There has to be balance, and balance is best for this 5% where we are getting highest, and after that it's reducing a lot. If you are allowing more, and it will go down.
So if there are no more questions, let's thank the speaker again.
Thank you.
So in the continuation of the talk series in this session, I think my work also aligning in that way. So the title is Anisotropic in-plane thermal conductivity of freestanding few layer RES2, and I am from IC Bangalore Science Department. So if we talk about the RES2 crystal structure and band structure, so it's very different from other 2D TMDs materials. If we compare with MOS2, it has not, it don't have one H structure hexagonal, but it has distorted outer structure due to the PL distortion in the RE atom zigzag chain we can see here, and due to this it has a good anisotropic property in its physical properties. We can see here also, due to that effect there is a minimal effect of the interlayer coupling in its optical and electrical responses, and I will show you next slide. And that thing we can see here, the interlayer distance is very low in the RES2 in compare to MOS2. So it's very less coupling in the interlayer, and in no layer dependence in Raman and PL in terms of peak position. We can see here, if we compare with MOS2, like this MOS2, we know in bulk the difference between E12G and A1G mode more, but in this RES2 it's around same position. In PL also we can see its PL position is not very changing, and intensity is if we compare with other 2D TMDs material, group 6 material, so it the shows some number of layers increasing, then the peak position changes, but it has a constant peak position here we can see. And in RES2 we can see the opposite trend is also there, and it is saturated in the thickness dependence. So it's a very interesting material to study the thermal conductivity, and it shows stacking order in this material, and we can calculate that stacking order using Raman spectra. In Raman spectra we can see mode 3 and mode 1, like this mode I will show in my experiment. So mode 3 and mode 7 difference, if it's 17 that's mono layer, if it's higher than 17 it's AB, if lower than that then it will be AA stacking. So the motivation came, people have done some work, but not in monolayer, bilayer or trilayer limit, few layer limit. So 2 studies were there. So some people have done using TDTR method, FDTR method, different method. For these methods work for the thicker sample. So our goal was, can we do some freestanding samples, thermal conductivity for few layers, stacking order effect also, can we see. So for this study we use the optothermal Raman technique, and in this I will show the sample fabrication. So this is very simple fabrication, not very simple, but the method is simple to calculate the thermal conductivity. So this is a sample schematic, how we make the sample. There is a SiO2 Si, then we etch using Ri, then put RES2 on that. So to calculate the thermal conductivity of the material, we just calculate the power coefficient, temperature coefficient in the suspended region. Then using this formula given by Balandin, it's a very well known formula for the thermal conductivity 2D material using Raman thermometry. So we have used this procedure to calculate the anisotropic thermal conductivities. This is the sample. This is a tri-layer of RES2 is suspended upon on the array of holes. 5 places we can measure here. This the thickness is around 3.5 nanometer. We can see that it's suspended, well suspended, and supported and suspended has some difference due to the strain in plane strain, and PL is enhanced also in the suspended case, which shows it is well suspended, and we can study this optothermal Raman technique. So in one more thing we have to see in this material, the crystallographic axis we have to see, because I have to see the anisotropy in the material. So we perform the polarization dependent Raman spectroscopy to see where the RE chain or B axis people in generally tell in this material. So where the mode 5, like this mode has maxima along RE chain, which is called B axis. This we can see in the black double arrow. So this is the RE chain confirmed by the polarization dependent measurement, and I was telling that stacking order we can calculate see with the difference between the third and second first mode. Here we can see this is the 14.02, so it's AA stacking. So we will perform the temperature dependent and power dependent measurement on this sample AA stacking. So we have two scenarios here. In one case, the laser polarization of the laser polarization will be parallel to the B axis, or in other case it will be perpendicular to the B axis. In both cases we have performed the temperature power dependent measurement and calculated the first order power coefficient, which shows the anisotropic nature because it's different in the different axis. Similarly, we have performed the temperature dependent power Raman spectra for the same sample, and it also shows anisotropy in its temperature coefficient due to the anisotropic thermal dispersion. So using that formula, we have to calculate the thermal conductivity, but in this formula there is a actual absorption of the material. For that we have performed the white light reflection measurement to calculate the actual absorption of the material, and for that we have also taken care the polarization of the white light and calculated the our absorption in parallel to B axis and perpendicular to the B axis. So we have using this formula we have calculated the thermal conductivity, and we can see here the thermal conductivity has some different value in both directions, like there is a anisotropy in the our thermal conductivity. Similarly, we have done 5 samples in different stacking also, different thickness also, like we have seen here 3.5 nanometer 2 sample are there, where the A and AB shows some different in plane direction and stacking dependent thermal conductivity, and in A there is some more thermal conductivity in compared to AB stacking. With increase in thickness we can see the in plane thermal conductivity increasing, but anisotropy is maintained. So for that the experimental values we have some theoretical support from our collaborators, and we can see here the calculated phonon velocities are different in different orthogonal direction, so anisotropy is maintained, and we can see in A and AB also the difference in anisotropic phonon group velocity. So there is AA has more thermal conductivity and AB is less thermal conductivity, and here we can see the phonon lifetime we can relate with the Gaussian parameters. So AB stacking indicates more phonon scattering, so greater harmonicity, leading to lower phonon lifetime and reduced thermal conductivity. So this calculation supports our experimental findings. So in summary we can tell we have made the freestanding fuel air RES2 for optothermal Raman technique. We have measured the A and AB stacking and the thermal conductivity in the thickness dependent nature, and for to support that experimental values we have some DFT calculation which supports well, and it is archived, it's under review, this work. And I acknowledge my professor and my collaborator in this project, and my fellowship and institute and other facilities, clean room and characterization facility. Thank you.
Questions?
So this RE is what, rare earth or some element?
ReS2 rhenium material is, yeah, and S2 sulfide.
You prepare their thin films.
Using exfoliation, mechanical exfoliation, we buy the material and exfoliate using mechanical exfoliation.
So is the thermal conductivity lower than say bulk materials for your?
Yeah, in reducing the, we can see the trend also, but increasing the thickness will increase the thermal conductivity like this. But it will sometimes saturate also in higher thickness, but in lower thicknesses it has a lower thermal conductivity.
So this thermal conductivity you have measured by a technique, say Raman.
Raman spectroscopy.
Is it comparable to say other conventional techniques?
Yeah, it's there. Yeah.
So any other questions?
So why did you use this? Why did you remove the SiO2? Why did you use the freestanding?
Yeah, that is a very good question in this study. I haven't included due to the 10 minutes talk. So, yeah. So when the substrate supported region will be there, like here I have done here. If I will perform the temperature power dependent measurement, then I will not get a shift in the power dependent measurement, because there will be faster dissipation of the heat. So to avoid that, I have to do a freestanding nature, because there will be no heat dissipation. It will be very slow. So I have the time to measure the shift in the power dependence.
But you mentioned that this anisotropy is coming due to the different phononic velocity along different directions. Right?
Yeah.
But this freestanding model, this device will also create strain in the material.
Yeah, strain is there, but we are just seeing there is means some difference is there, but we are not very focused on the strain, because we are measuring after we are thinking that this is the now our setup. Now we measure the thermal conductivity, but strain is there definitely.
Strain would be there. So
Yeah.
is there any contribution from this?
It will be there, but we are neglecting in our measurement. We can incorporate in our measurement. There are many papers we can see those effects, and they have incorporated that effect also. Some minor changes in correction will be there.
And what will be the monolayer thickness for RES2?
This is AFM, but in theoretical limit it will be around 0.7, 0.75 something.
Yeah, because you said tri-layers. And
Yeah,
this is
yeah.
3.5. So this is 1.
Yeah,
monolayer
but
is around
the
1.1 nanometer.
interlayer distance will also work in the AFM, na? So we cannot multiply 3 layers.
Okay, so we can discuss, I think, further outside. Thank you very much for the talk.
Thank you all.
Let's thank the speaker again.